So thanks for the introduction, and also thanks to the organizers for putting this nice workshop together. This is joint work with Shusen Wang, who's now at Stevens Institute, and Michael Mahoney. And this workshop brings together people from a lot of different research specialties, so I'm not going to assume that everybody necessarily knows a lot about the Bootstrap, so I thought it would be kind of helpful to make some very high-level remarks. So conventionally in statistics, the way we think about the Bootstrap is it's just sort of a general tool to do inference on randomness in data, and we often think of it as something that's computationally intensive. In fact, sometimes the word computationally intensive methods is used as a keyword to label research papers on Bootstrap methods. The perspective I'm going to take in this work is almost reversed. So I'm going to use the Bootstrap to do inference on randomness in an algorithm. And also the goal will be to use the Bootstrap to enhance computation. So again, this is sort of a very unusual way of thinking about the Bootstrap from a statistician's point of view. Another thing is that the Bootstrap is just an extremely flexible and general purpose tool, and I think there's a lot of potential for its sort of broad application in randomized numerical linear algebra and related fields. So I kind of want to use this talk as an opportunity to sort of sell that point to this community. And to sort of underscore this, I want to sort of share an amusing remark that's at the very end of Efron's 1979 sort of seminal paper on the Bootstrap. So if you read all the way to the very end, this is the last sentence of the paper. It says, "I also wish to thank the many friends who suggested names more colorful than the Bootstrap, including Swiss Army knife, meat axe, and my personal favorite, the shotgun, which, to paraphrase Tukey, can blow the head off of any problem if the statistician can stand the resulting mess." So I think nowadays we can tolerate the mess a lot better than they could in 1979, just due to the fact that distributed computing is becoming ubiquitous. So I think the Bootstrap's a pretty cool thing. I don't really need to go through this slide very carefully in light of everything that's been said in the past 2 days. So we all know that randomized numerical linear algebra has been intensively studied now for quite a while, and there have been highly optimized algorithms and so on. But of course, in exchange for getting these speedups over more traditional algorithms, we pay a price, which is we have to tolerate some random error. All right, and this is the issue I really want to focus on. So if we compute some randomized solution, how large is the error for that particular solution? Okay, not in the worst case, not in some other general sense, for this particular solution. That's the error that I want to study. So the prevailing sort of theoretical viewpoint in this area has been to derive theoretical bounds describing the errors of solutions. And this is a very useful thing. It gives us a lot of insight into the factors that influence the quality of the output. But there's some sort of essential limitations to this kind of approach. So often it's done from a worst case point of view, so it may be pessimistic for any particular problem. The bounds often involve constants, which may be, even if you can whittle them down to something nice, they are often still conservative, or even worse, they could involve unknown constants. And likewise, they typically do not take advantage of the structure that may be unique to your given problem. So for these reasons, it's often difficult to use these theoretical bounds in any sort of numerical sense in a given problem. And so what I want to pursue is an alternative. So I want to numerically estimate the error of a given solution. And in certain areas of applied math, this approach has a name. It's often called a posteriori error estimation. So in areas like numerical PDEs or finite element methods, this is a fairly well-developed thing. There are even some textbooks written on it. In numerical linear algebra, or randomized numerical linear algebra, maybe not so much. There are a handful of papers that have considered this at least a little bit. And in fact, among these few references, some of the people are here. But nevertheless, I would say that it's safe to say that this approach is underdeveloped, and there's quite a bit of potential to explore what you can do with it in a broader variety of algorithms. So I'm just going to focus on two sort of prototypical linear algebra methods or algorithms, so just matrix multiplication and least squares. And I'm going to break the talk into more or less two disjoint pieces. Okay, so I'll just kind of outline the setup. So I have two extremely tall matrices, A and B. They're deterministic. Okay, so in all of the problems, I'll consider the inputs I'm viewing as deterministic, even though they could obviously be data. I'm not going to consider that source of randomness. I'm only going to focus on the randomness in the algorithm and or the randomness in the Bootstrap method that I'll propose. Okay, so the number of rows is n. That's a very large number. The number of columns is d. It's relatively small compared to n. It could be large in an absolute sense. And let's say we want to compute A transpose B. All right, so as we know, the cost of ordinary matrix multiplication is n times d squared, and we want to bring that down. So we do, I guess, what's now, commonly known as sort of a sketch and solve kind of thing. So we'll form sketches out of the original matrices A and B. I'll use the letter T to denote the sketch size. So I'll bring the n rows down to T, and I'll denote the sketches as A tilde and B tilde. And for the purposes of the Bootstrap, there's really only two basic properties that I'll need for the sketching matrix. So I'll just need that the expected gram matrix is the identity, and that the rows of the sketching matrix are essentially independent. Okay? Conceptually, that's really all that matters. When you look into the fine-grained details, when you derive bounds and so on, there are some different technical consequences for different choices of sketching matrices, but I think that's sort of a second-order consideration. All right. So how do we choose T? Okay, so there's a direct relationship between the choice of T and the quality of the sketch product. All right, so of course, the quality is going to improve as T gets bigger, and that's essentially a consequence of the law of large numbers. So if we expand the gram matrix out as a sample average of rank 1 matrices, independent rank 1 matrices, okay, and we know that the expectation is the identity, this is going to get closer and closer to the identity with high probability, and therefore the sketch product is going to get closer and closer to the true one. All right, so that's clear at a conceptual level, but what does this actually look like in a real example? I think this plot gives a lot of insight into what's going on at a sort of in a sort of statistical way. So let's focus on the left plot first. The way I've generated this plot is as follows. So I incrementally add one row at a time to a sketching matrix. Each time I add a row, I compute the exact error for that particular sketch against the true product. So of course, this is not something you can do in practice. This is just to illustrate what's going on. So as you expect, the error generally improves as the sketch size gets bigger, but there's some fluctuations along the way. Now you can imagine repeating that entire experiment many, many times, and that's what the right plot shows. So the right plot shows many independent copies of the sample path that's on the left, and you see there's actually quite a bit of variation. And so, I mean, another way to think of this is each person in this room could have their own sample path, and so this reflects the quality of all of our sketch estimators in aggregate. And at any given sketch size, what any one of us wants to know is, what's an appropriate error level such that I'm likely to be below that for some tunable probability. Okay, so there's a name for that. It's called a quantile, or let's say the 99th percentile. That's what the thick black curve is. All right, and I think this quantile function or quantile curve is a very useful way of thinking about the trade-off in a sort of very quantifiable and estimable way. All right, and I'm going to use the letter epsilon sub t to denote the random error variable. Yeah.
Does it look very different if you plot, like, just for mean square error? Or?
I think conceptually the choice of the norm doesn't matter so much. I mean, the scaling will change, et cetera. But I would say as long as the norm or error functional more generally is a smooth functional, then this kind of picture arises. And in fact, this is a very, very generic sort of thing. So I mean, I've done things with random forests. I've done things with least squares. This is sort of very generic. Okay. All right, so I'm going to call the quantile function q sub 1 minus alpha of t. So the probability that I'd like to have for an error bound, let's say, is 1 minus alpha. And if we had access to this quantile function, we could do two things with it. So for a given sketch size, it gives us a particular bound with high probability. But there's another way we could use it, which is sort of in a predictive sense. So if we have some error tolerance that we'd like to achieve, this quantile function will allow us to look ahead and forecast what sketch size we'll need to get to in order to achieve that. So both of these, I think, are interesting. And this is what I'd like to estimate. So that's the sort of the well-defined statistical problem that I'm proposing to solve. I want to estimate this function. And here's why it's not easy. So I constructed this Fick-Black curve based hypothetically upon many experiments, right? But in real life, we only get one A tilde and one B tilde generally, or at least that's what we want. We only want to run the sketching algorithm once. So it might seem almost impossible that you could approximate this thing that comes from many repeated experiments just from a single experiment. And that possibility is, in a sense, what is so remarkable about the Bootstrap. Okay, so the Bootstrap is what makes it possible to do that. And another important consideration is that we're computationally constrained, right? I don't have an infinite amount of resources to compute this quantile function, even if I come up with something clever. It needs to be cheap enough so that it doesn't outweigh the benefit of doing sketching in the first place. Okay, so I'll definitely keep track of this cost as things go along. And again, just to make this point clear, we never get to see any of these curves in practice. Okay, so this is just for illustration. All right, so let me give you just a little bit of intuition for how the Bootstrap algorithm will work. So let's imagine for the moment we could generate independent copies of the error variable. Of course, we can't do that in particular because it depends on the true product. But if we could, let's say we could generate 100 samples, well, we could take the second largest of them, and that would be a natural estimate of the 99th percentile, and that would be quite effective. Of course, we can't do that. So in essence, what the Bootstrap tries to do is to generate pseudo samples of this variable, plain and simple. And then once we've generated enough pseudo samples, we'll take the quantile of those. All right, so here's the algorithm. I could fit it easily all in one slide. So the input is an integer m. That's the number of samples I'm going to generate. And then the only other inputs are just the A tilde and the B tilde. All right, so here's the loop. I'll draw a vector of numbers without replacement from the set 1 through t. I'll take those indices, and then I'll plug them into my sketches, and I'll use those to form, or I'll take, rather, the rows of A tilde and B tilde indexed by these random integers, and that will give me two new matrices, A tilde star and B tilde star. So there's going to be replicates of some of the rows of A tilde and the B tilde in the starred versions. Then I'll take the norm of the difference between the starred product and the unstarred one, and I'll view this as a pseudo sample. So for each iteration of the loop, I get one of these starred pseudo samples. Then after the loop is done, I take the desired quantile of those samples. So this is the whole thing. It's really that simple. So maybe I should pause for just a moment in case there are any questions. Yeah.
A stupid question. Why do you take the quantile? Why don't you just look at everything?
So, I mean, I guess it depends on how you want to formulate the problem. So there are other ways, certainly. You could look at variance instead of quantiles. That makes a lot of sense too. But I mean, if we agree that our goal is to estimate that population level quantile function, then taking the empirical quantile is sort of a natural thing to do. But there's certainly other things you could try. So, yeah.
So is it possible that you just regenerate many replications of the sketching matrix, then you get the A star rather than you do a subsampling?
Right, but so indeed, so that would basically be what I was mentioning here. So so you're saying do actual sketching many times.
Yeah, but the center is not A transpose B, it's A tilde.
Oh, I see what you mean. Yes, you could do that. I believe though that the resampling is actually much cheaper, and we'll get into that maybe more in a second. Yes. So in particular, yeah, you're not going to have to generate a new sketching matrix. You're not going to have to do any new matrix multiplication with a new sketching matrix. That's kind of baked into this sampling mechanism. Yes.
Also, your problem definition was to find out the accuracy of A theta B theta, right? So this thing wouldn't really find the accuracy of this particular sketch. It would just find out the efficacy of sketching t times. But
It would effectively give me independent copies of that variable, roughly. So I could imagine that working, but it wouldn't. Indeed, it wouldn't give me an error estimate for this particular sketch, but it would give some reasonable way of approximating the quantile function. Okay, so we'll just move on. All right, so just to be accurate in how I present this project, in the paper we analyze a slightly different version. So there's many flavors of Bootstrap, if you will. So this is what's sometimes called the multiplier Bootstrap in the statistics literature. At a conceptual level, there's not really that much stuff that's different going on. In essence, the sampling is done using Gaussian variables. This is really just for convenience of analysis. If you do experiments, the results are effectively the same. So I'm just mentioning that, so just so you don't get confused if you look up the paper. And there are some interesting differences, but at a high level, this is not so different. So I won't go into the details, but there's a relatively simple way to see why this is mimicking the previous Bootstrap sample. Okay, so now I have an algorithm, but how much does it cost? So what I want to argue here is that there's a really simple but effective way to dramatically reduce the cost of sort of this basic Bootstrap that I just proposed. And this is based on extrapolation. So in applied math or numerical analysis, extrapolation is a very classical idea. So the thing I'm getting at here is closely related to Richardson extrapolation. So the central limit theorem tells us that this quantile function should scale like 1 over square root of t. Okay? And that's really useful because what it means is if we could estimate a point very early on this quantile curve, then we can just rescale to get everything thereafter. All right? And what's kind of amazing is that as simple as that is, it works really well. Okay, so let's say I generate some little sketches of size t naught. Those are going to be poor sketches, but I can still apply the Bootstrap to those and get an estimate. And then I just rescale for all t that are larger. Okay. And so, so basically I would be estimating a point here, even though ultimately I'd probably want a sketch size out there. So this t naught is just sort of an expedient. Yes?
That's only holding because your n is assumed to go to infinity, right?
Right. So this is a delicate question. I mean, the t naught needs to be of some moderate size, right? I mean, you want t naught to be maybe at least 50 or 100. It doesn't need to be huge, but it can't be just one or
Can you
two.
apply instantiations of the central limit theorem, Chernoff-Hefting type bounds here to get...
Right. So I'll have a few comments about the analysis later. So the analysis involves a lot of things, but we can get into that. All right. All right. So let's be a little bit more detailed about the cost. So the cost of sort of generic sketching algorithms for matrix multiplication looks like something like this. So you have the cost of doing ordinary matrix multiplication on the sketches, and then you have this additional term that comes from implementing the sketch itself. So for instance, in the case of randomized Hadamard, that's what the second term looks like. And this is the cost of the Bootstrap. So at each iteration of the Bootstrap loop, I do ordinary matrix multiplication, and that gives me the t naught times d squared, and then I do that m times. So basically what I want is for this cost to be no greater than the first one, and that happens as long as the number of Bootstrap samples is not too large. Okay, so here you can see why the extrapolation helps, because it says that as long as the initial sketch size is relatively small compared to what I'll ultimately need for an accurate sketch, then that gives me quite a bit of runway for picking a decent number of Bootstrap samples. And what's empirically nice, so I'm just making an empirical statement here, is that in a lot of problems, 20 Bootstrap samples is perfectly adequate. Okay, so this, there's nothing sneaky going on here. Okay, so in fact, you could almost think of the number of Bootstrap samples as being O of 1 for practical purposes. maybe logarithmic or something. Okay, and furthermore, we're assuming n is large, right? So if n is much, much larger than d times a small initial sketch size, we're in good shape. Yes.
So how are you supposed to estimate the 99th percentile with only 20 samples?
Yeah, okay. So you can use an interpolation rule. So I think for the second largest among 20 samples is going to be the 97th or 8th. You know, it's not going to be quite 99. But there's a if you use MATLAB or something, there are simple interpolation rules to get the 99. This is a very minor detail, but indeed that's a legitimate point. So okay. I'll just say a few comments about the theory. There's a lot that could be said about the results in this paper, and in fact, most of the paper is theoretical. To formulate to describe the performance of the Bootstrap in a non-asymptotic way sort of requires some care. So here's kind of a natural way of doing that. So I have a random variable whose distribution I'm interested in, and I can consider the distribution of the Bootstrap sample conditionally on the sketch that I drew. And if you compare those two distributions in a metric, there's typically a direct way of relating that to the distance between their quantiles. All right, and I scaled them by a factor of square root of t just in the interest of making comparisons with central limit theorem. This is just sort of a technical thing. And the types of sketching matrices for which the theory works, there's a variety. You can do IID, sub-Gaussian. It's maybe somewhat idealized, but still interesting. You can do length sampling, and the theory also applies to randomized Hadamard transform. Here's what one of the results looks like in the sub-Gaussian case, just because it's a little bit simpler. I'm using the entry-wise maximum absolute value norm as my norm for the error variable. Okay, certainly we could talk about exploring other norms, but even as simple as that norm may seem, the theory is surprisingly involved. And this is what the distance between the Bootstrap distribution and the actual distribution looks like with high probability, right? So this distribution here on the right, that's a random probability distribution, and therefore this distance is a random variable. And I can concede that maybe in the context of numerical linear algebra, the shape of this bound might look a little unusual. In the high-dimensional statistics literature, when analyzing problems involving multiplier bootstrap methods, this type of bound is actually not so uncommon. So I think it's important not to take the exponents in too literal of a sense. I think at a first pass, the way to think about this is there's a problem-dependent scale factor, there's a dimension-dependent factor, and there's a sketch size. And basically, the result at a minimum is telling you as long as the sketch size is sufficiently large compared to these other two factors, the bootstrap's going to work. Okay, so
Excuse me, so if
Yes.
I go ahead at the beginning of my experiment and divide all the matrix entries by 1,000,000,
yes.
right? Then,
Yes.
then that bound looks a lot better, doesn't it?
Indeed. So it's natural that you should have a problem-dependent scale factor because if you change units, it's going to be if you blow everything up, it's going to be a lot harder to get a good accuracy. So yeah, I think maybe it would be simpler if you scaled things so that these norms are 1 even. I don't think this is something to worry about too much, but I think it's not unexpected that there's a problem-dependent scaling
You
factor
think I
here.
can fix it?
Yes, and also this function h is a little bit where does that come from? Why is that there? So let's not spend too much time on this. There's a lot of other theory in the paper that I'm not going to talk about, and also there's some interesting ideas that I wish I could talk about, which I think are novel contributions, but in the interest of time, I'll skip over all of that.
What is that distance?
Oh, right. So the Levy-Prohorov metric. So there's actually a variety there's a whole bunch of probability metrics or metrics on probability distributions that you can think about. They all have different advantages and disadvantages. This one is a particularly nice one because it metrizes weak convergence. So a sequence of random variables converges in distribution if and only if the distributions converge with respect to that metric, so this is sort of a natural one. And it also relates naturally to quantiles, but that's a minor point. Okay, so let me say something empirical, and I think in some ways this is one of the more exciting slides. So here's what's going on. The two plots just refer to two different kinds of sketching matrices. So the experiment on the left involves randomized Hadamard transform. The experiment on the right involves length sampling. My full matrix A has 60,000 rows and about 800 columns. I'm using an initial sketch size of 390. That was chosen just because it's half of D. So 390 is obviously a lot smaller than the full number of rows, 60,000. So that shows you that you can really start out with quite crude sketches. The number of Bootstrap samples, as I mentioned earlier, I'm going to take to be 20. So really what's going on is I take two really small sketches. I apply the Bootstrap. All right? The black curve represents the true quantile function at every t. The blue curve is the mean of the Bootstrap estimates over many repeated experiments. The green and the yellow are one standard deviation away. Okay, so here is where the Bootstrap actually gives us one estimate, and the rest is all from the extrapolation rule. So I think this is kind of remarkable that we can predict quite accurately what's going to happen well past 10,000, starting out with only 400. Okay, so the extrapolation is a really useful thing, and again, it works kind of regardless of what kind of sketching matrix you use. I mean, there's a little bit of dependence. You can look at those details in the paper, but more or less, the details of the sketching matrix are not so critical.
So, but Miles, if you took that experiment and you rescaled, like Lisa suggested, by 1/1000.
Yes, so indeed. So I forgot to mention, this experiment, we scaled the Gram matrix, so the largest absolute value is 1.
Oh, okay.
So indeed, yes, yes.
So just put this in context. If I just estimated 0, how much air am I going to get? Like, is the air going down just because the expected error is going down as well?
So you're saying if the A matrix is 0?
No. If I estimate how much air I'm going to get between A tilde B, A tilde transpose B minus A transpose B, right? And I just estimate that error is 0. Is my plot going to look like this, or is it going to be dramatically worse?
So I mean, in fewer words, are you asking if the estimate is vacuous? I don't think so. I mean, so I would need to think for a few minutes to give you an accurate answer to that, but I don't think 0 is gonna work. Yes.
So assume A and B have some structure assumption, okay, which very often happen. Okay. So how can you design some sampling scheme or projection random sketching matrix to respect that structure? Is there any way of doing that?
There's a lot of things that could be done with. That's a good idea. What's nice about the Bootstrap is that in a lot of ways it's agnostic to the structure of the matrix. It works reasonably well for a lot of things. I imagine there's possible improvement that you could get in structured cases, but that's something I haven't looked into in detail. So I don't actually have a lot of time left, and there's still the entire least squares portion. So just bear with me, and I'll try and get through the important points quickly. Okay, so in the least squares case, I'm going to look at a tall A matrix, a long B vector, and I want to solve an overdetermined least squares problem. Again, n is much, much larger than D. I'm going to use the sketches, and an important point is that, okay, there's more than one type of sketching algorithm you can use to solve this problem. There's the sketch and solve kind of thing due to Jonas Mahoney and Muthakrishnan. There's more recent proposals that are sort of more like quasi-Newton methods. But what I think is really interesting is, even though these algorithms are quite different, the Bootstrap still accurately estimates the errors of either of them. So you get to take your pick, and the Bootstrap will still do its job. Okay, so I think that's enough here. The problem formulation I'll think about in the least squares case is pretty much the same. I want to estimate the quantiles of the error variable. Okay, now again, you can pick some norm on the solutions. The quantile function will depend at a technical level on that norm, but let's not worry about that for now. Okay, so we have this intuition for the bootstrap that we're generating pseudo samples. In the least squares case, I think a nice idea to keep in mind is that you can think of the bootstrap as doing something sort of in a parallel universe, where the original sketch solution in the parallel universe is playing the role of the true exact solution, and the bootstrap is sort of constructing this perturbed, kind of scuffed up version of the sketch. And if the difference between the scuffed up version of the sketch and the sketch is statistically similar to the fluctuations of the actual error variable, then that's a way of thinking about the bootstrap and if it is doing its job. Okay, here's the algorithm. So this is more or less the same template that I described for the first version of the bootstrap. So I'll draw t numbers with replacement from the index set 1 through t. I'll use those indices to extract a new set of rows from the original sketches or entries of the vector b tilde. I'll solve the associated least squares problem with the starred inputs. Okay, that'll give me a starred solution. Then for that particular iteration of the loop, that'll give me one bootstrap sample by taking the norm of the difference between the starred solution and the unstarred one. Then after I've done m iterations of the loop, I'll again take the desired quantile of those numbers. Okay. Now, the Gaussian multiplier bootstrap that I described earlier actually is not appropriate in this setting. It is important that I do the sampling without replacement in this setting, but that's just something to mention. And one other thing is that this template more or less works in the same way for the iterative Hessian sketch algorithm. There's a few minor details that have to be modified, but it looks more or less the same. Computational cost, a lot of the same high-level remarks apply again. So one important thing is that the cost of the bootstrap is independent of the large dimension n. That's great because it means it's highly scalable. And there's an easy way to see that just because the bootstrap never sees the full inputs. It only sees the sketches. Again, in the least squares case, 20 bootstrap samples is typically adequate. I didn't mention this detail before, but the bootstrap samples can be generated in an embarrassingly parallel manner. None of the bootstrap samples have to talk to each other. Furthermore, the communication cost is pretty small because you're only communicating the sketches. And in fact, it's even better than that because you're only communicating the initial sketches. So those are quite small matrices. This is something you could do on a laptop, perhaps. And even better, in the least squares context, the bootstrap computations have free warm starts because at each iteration of the bootstrap loop, you're solving a new least squares problem. The bootstrapped solution is going to be close to the original sketch solution, and therefore you can use the original solution as a warm start if you choose to.
Can we wrap it up in like a next minute or
So,
so?
right. So, okay. So here are some plots. I'm using extrapolation here as before. In the iterative Hessian sketch, I'm going to use a linear extrapolation rule rather than the square root of t rule that I described earlier, and that's just because this particular algorithm has a linear rate of convergence. That's all I'll say. We have some reasonable theory. I don't have time to get into, so I'll just make some closing remarks. The bootstrap is a flexible approach to error estimation that can be adapted to a variety of problems. It provides a practical alternative to worst-case analysis, and it's naturally adapted to the inputs that you actually have. The cost of the bootstrap does not outweigh the benefits of sketching, and in fact, there's a lot of ways to speed it up. You can use extrapolation. The computations can be parallelized, etc. And the numerical performance is encouraging, and it's supported by theoretical guarantees. We have some papers. There's a paper on matrix multiplication and least squares, which just came out in ICML. I also have a paper quite different from this, but uses the same ideas in the context of random forests, and that will appear at Annals of Statistics later this year. So thank you.
And why don't we just take questions offline? We have a break now, and thanks, man.